Our first talk today is entitled DeepWeather, Using Deep Learning to Produce High-Resolution Weather Forecasts over New Zealand. And for this talk, please welcome up Emily O'Riordan.
Tēnā koutou katoa. I think I've only got 10 minutes, so apologies if I go rapid fire. But I'm going to talk to you today a bit about my research. So a lot of the talks have been about good e-research and facilitating e-research. And this is just an example of what kind of research that can actually lead to. So I know that we'll probably have quite a lot of people from NIWA and that sort of thing, so bear with me. I'm just going to quickly go over the basics of how weather forecasting works. Essentially, we have these global models, and these global models discretize the whole globe, into grid cells. We need to solve a whole lot of very complex equations that tell us a lot about the state of the atmosphere in each and every single one of these grid cells at every single time step that we're interested in. So obviously, there's quite a lot of compute needed to do that, and that's at the global scale. To then forecast the weather in New Zealand, we take that huge grid that we have and we make a smaller grid nested within that over our area of interest. So here you can see one over New Zealand. And we resolve those equations in this new grid that has smaller sized grid cells. So we get a bit more of a detailed outlook of what's going to happen. And sometimes we nest grids within those nested grids. So you can quickly see how this becomes a really complicated problem and needs a lot of compute resource. The cost of doing this kind of thing, so Met Service are a partner on my project. Their 4-kilometre resolution national weather forecasts use about 259 core hours per run, and they run that twice a day, just using the most up-to-date global weather forecasts. That's running at a 4-kilometre resolution. You can see if we look at something like Christchurch at 300 metres, which is this little tiny green box down there, at a 300-metre resolution, that's using an awful lot more compute for such a tiny, tiny amount of the country. So obviously having a nationwide dynamical weather forecast at that kind of scale is just infeasible. This is a comparison of those two different scales. So the top scale is the 4-kilometre resolution weather forecast that's used nationwide, and the bottom one is the 300-metre resolution weather forecast over Banks Peninsula. Obviously, the top one does tell us what's going on, and forecasters are trained to sort of translate that to more local information. But if we could get weather forecasts like the bottom one, that would tell us a lot more. You can see how the topography influences the temperature, and on the other side over there, that's precipitation. And it's especially important for things like precipitation, things at convective scale, because that can help us model extreme weather events a lot better. So when things like the cyclones came through and the anniversary floods of last year, if we could model things at this kind of scale, we'd be more likely to hopefully pick things up with more accuracy. So yeah, those things are too costly to do. So that's kind of given rise to a boom of using deep learning within weather forecasting. This is on a global scale. So there are some papers here that have been released in the last year or so. And as you can see, these have got some big players in. There's NVIDIA, Huawei, and Google are all participating in this field of research. And GraphCast, which is this learning skillful medium range, blah, blah, blah paper, that was the first paper to actually beat some of the dynamical weather forecasts that are used by some of the global centres. These are really, really quick to run. Once they've been trained, you can run them on your laptop. So it's better than the amount of time that's spent running these dynamical forecasts that we saw earlier. But training them is no small feat. The GraphCast paper that I mentioned took 4 weeks to train with 32 TPUs. So it takes a while, and it's not accessible to everyone to train that kind of model. My research, I'm looking at producing weather forecasting over New Zealand in particular, rather than at a global scale. And I'm looking at making it as high resolution as hopefully we can. I'm not going to go too much into the architecture about this deep learning model, but essentially I feed it some lower resolution information at 2 different time steps and some higher resolution at a previous time step in the hope that it can then produce a high resolution forecast at the next time step. So I don't know if that came out properly, but essentially it's a deep learning model that's hopefully going to produce high resolution weather forecasts. And I can happily talk about architectures and things like that at some point if you're interested. But obviously training these models like you've just seen with the GraphCast one requires a lot of compute and a lot of resource. Unfortunately, this project is MBIE funded, which means I'm lucky enough to be able to use Nessie. So I've got that great resource, and I've got the Nessie team there who help me with all of my questions, because HPC is quite a new field to me. So thanks to them for their help with this project. Some very preliminary results are shown here. So essentially, if we just assume that the top row up there is our input to the model, the next row down is what we're aiming to produce. These are the temperature fields, and this is actually using US data. You can see this the third row there, that's a model output. It does very well in producing the first hour that we're interested in at a high resolution. But then when that gets fed back into the model and we have an autoregressive model at inference, we lose some of that sharpness and there's noise in the model. We then went and retrained the model to be autoregressive within its training. And you can see that it produces better forecasts when we look at a longer horizon, but we do lose some of that initial sharpness. So there's still some work to be done here, but these initial model outputs are promising, so fingers crossed we'll get some good stuff coming out of this research soon. As I said, thank you, I used US data there, and that's because we don't actually quite have high enough resolution weather data here in New Zealand at the moment. There's just not quite the resources and the capacity to have that data. So this is a slight tangential project of mine, but something else that I'm working on, which is essentially trying to take lower resolution data, make it high resolution, and also map it to the station data that is available in this country, which again is another deep learning model. So even more compute and resources needed for this kind of project. But here is, again, some preliminary outputs. And you can see we've gone from a 9-kilometre model to a 1-kilometre model in the middle. And the nice thing about the deep learning method that I'm using, which is called a convolutional neural process, if anyone is interested, is it also outputs its uncertainty. So we get standard deviation coming out from the predictions. We can say, yeah, we think this is probably what happened, but we really, really don't know down here in the south. You know, there's a complex topography, there's less station data there, but up north we're a little bit more certain. And these are, like I say, very preliminary results. So fingers crossed, more to come soon. But I'll leave it at that. Thank you very much for your attention.
Thank you very much, Emily. Are there any questions from the audience?
Hi. Are the models trained on a certain location, or are they general purpose?
So the weather forecasting models, they're being trained over, well, like I say, currently I'm using US data. And the way that I'm doing it to get that data to fit into memory is I'm just chopping up all of the data in the US. If you use a purely convolutional model, that means that at inference you can then feed in the whole map of the US. But currently I'm just using the whole of the continental US in my models there. Eventually, hopefully when I've got these models, I will do the same over New Zealand, but I will again probably chop it up. New Zealand is a funny shape, so if you take the whole square like you see here, you get a lot of C and a lot of redundancy and a lot of memory usage there that you probably don't want to be using. So yeah, it will be a nationwide model.
So, but do you think the model is learning specifics about locations, so it'll learn
Yeah.
how to predict in Wellington.
Yeah, so I don't know how well you can see that from there. You can see these station data here. It's definitely more biased to areas where there's more stations available in this specific project here. In the other project, I've found that the more complex the topography is, the harder it is for the model to learn, which is not that surprising. So yeah, there's definitely variability in how well it's learning.
Yeah, I guess if it's convolutional, it might depend on how it's done as to whether it's kind of trying to learn general rules or specific rules.
Yep. So we do feed it things like topography and like land sea masks and other try and counteract that. But like, yeah, if you have any further ideas, I'd love to hear them.
Okay, yeah.
Please join me in thanking Emily once more. And with that, I would like to welcome to the stage our next speaker, Andrew Wilson. Andrew's topic today is software development challenges and best practices in an instrument data service.
So, hi everyone, I'm Andrew from the Centre for eResearch at the University of Auckland, and welcome to my talk. So, just to give a bit of background on me quickly before I start. So as I said, I'm from the Centre for eResearch, and there's plenty of us floating around this conference. So I'm in a team there which is working on a new instrument data service, so a system for managing instrument data, plenty of it. I come from a background in sort of commercial software engineering, and particularly with an R&D focus. So I joined the centre quite recently in August. So partly this talk is sort of giving my perspective as a newcomer and sort of some lessons learned. So just a quick outline. So I'll talk about my experience joining the project and the good, the bad, and the ugly parts. Then why this stuff is important and what the goals are. So just trying to sort of draw out some explicit goals from the experience. And then I'll be going through some individual software engineering practices that I think will help to meet the goals. First, just some terminology, and for anyone who's sort of a developer here, this will be meat and potatoes. Just wanted to quickly talk about a couple of terms I'll be using. So we're using the Git version control system, and that'll be familiar to a lot of people here. So a version control system keeps a history of all the changes that have been made to your code. It's kind of like track changes on steroids. And within that, there's a notion of a branch, and a branch is sort of a copy of your code where you can make changes independently. So within a particular repository, you can have lots of branches, so your code can effectively be in multiple states at any given time. And there's a convention adopted usually of a main branch, and it's just another branch basically, but it sort of usually represents the canonical state of the code. And then one thing you'll hear me talking about is the merge operation, which is an operation which combines changes from two branches, or brings them from one branch into another. So just starting with the good bits from joining the project. So when I started, had some very helpful background documentation for the project, sort of talking about the high level what and why, what the project was about and what the motivations were, which was very helpful to me. The team was following a sort of structured agile approach, and that'll mean different things to different people, but arranging things in sprints and tickets, and that I think that really helps someone coming in to get a picture of what other people are working on, what work is planned, what previous work's been done, and just a place to collect a lot of information about the work that's being done. So there's a high value placed on code quality. So there's a battery of checks set up to run on the code base, and helpful team members, which is always nice. So now onto the bad and ugly bits. So one thing that I sort of grappled with was some branch troubles. Basically, there are arguably better and worse ways to manage branches, and you can make things very complicated if you're not careful. So there was a tendency towards what I would call long-running feature branches. So basically, it's a branch which has accumulated a whole bunch of changes on it, and not all sort of related changes. And so there's a big divergence of the branch from your main branch, and you get into this sort of vicious cycle where changes accumulate on the branch, and then it becomes really hard to do a merge because it conflicts with so many things on the other branch. And so then, and in the meantime, the branch accumulates more changes, so it just gets harder and harder. So yeah, the branching was a big thing. The checks that I mentioned before, although individually very helpful, the way they were kind of set up was quite unwieldy. They were run as sort of pre-commit checks, and they would sort of, a few people on the team found that they would sort of interfere with your commit workflow, and often they would be skipped in practice for pragmatic reasons, which sort of defeats the purpose, I guess. So it's another issue. And then just learning the code base, and I guess this is a problem that anyone faces when they're coming to a new project. But yeah, just sort of trying to figure out if the code's in a running state and which branch is the canonical one to look at. And yeah, just how I could run the code. What's the entry point? Where can I sort of stick some breakpoints to run it and start stepping through? And so yeah, because of all these things, it took me a while to feel productive and feel like I was kind of able to contribute usefully to the team. Yeah, and so just drawing out some kind of broader observations. So yeah, as I mentioned, I've come from a commercial setting, and so moving into an academic setting, find that people wear more hats. So they might be doing development some of the time, and they might have various other responsibilities which don't involve sort of coding at all. So not everyone's sort of doing development day in, day out. They might be switching out. Yeah, and people from sort of more varied backgrounds. People have found, there have been different pathways into working in technology. Some people from a classic computer science kind of background. Some people have come to it through sort of their background in research and writing research code, which is very valuable in the team. But it does mean that not everyone's been exposed to kind of production development processes and workflows. And as we're sort of working towards trying to productionize the instrument data service, it's a bit of an issue. And another sort of broader point is that the tech sector, private and I imagine public, tends to have higher staff churn. So yeah, that means that teams will change regularly, and so the teams need to be kind of resilient to change. Need to try and onboard people quickly and sort of spread the knowledge around so that as much as possible, nothing's sort of locked up in one person's head. The dreaded bus factor one. So yeah, just trying to be more explicit about what the goals are here. I guess the first one is just quality code. So the code does what it's supposed to do, what we want it to do, and it's easy to understand and change without sort of breaking things or making it more complicated, ideally. And we want resilient and happy teams, so new people can get up to speed quickly and can contribute and feel confident doing so, and not sort of worry about breaking things. And skills and knowledge spread around, and ideally you want people learning from each other. Partly for that resilience, but also just so people feel like they're progressing professionally. And then just a structured and orderly development process, and that sort of helps people to understand where the project is at any given time. Helps the team to sort of estimate their capacity and the effort required to do any particular piece of work, and that sort of helps with planning out future work. So now I'm just going to sort of step into some individual practices, which I think can help with these things. So the first one is code review. So I guess in an academic setting, people here will be familiar with the idea of peer review, and this is basically peer review applied to code. So it's one of the most helpful practices for code quality, and I often hear people arguing that it's the most helpful, so pretty important. But one sort of underappreciated thing, or one thing that took me a while to sort of learn and understand, was that it's also a really useful avenue for knowledge sharing. So say you're reviewing someone's code, you might sort of learn something from how they've implemented a thing. You might be reviewing code that or part of the code base that you're unfamiliar with, so you'll gain some familiarity with that. And similarly, if you give some feedback or sort of spot any issues in the code, then that's a chance for the person who wrote the code to learn something as well. I think it's important with code review to try and focus on the big picture. It can be really easy to sort of nitpick and find sort of formatting issues and that kind of thing. But I think it is important to focus on the big picture. So basically, I think that means that you need to make it as easy as possible. So small change sets. So basically, if the review's a mammoth task that's going to take like a day, then it kind of just doesn't happen because everybody's busy. It's very understandable. And you want to try and remove the busy work as much as possible with automations. So just sort of hollow out that task with automated tools as much as possible. The next thing is documentation. And this is kind of a slightly vexed issue. I think I hear quite different viewpoints from different people on this. It can be very useful, documentation. Obviously, it helped me, like I mentioned before, it helped me a lot when I was starting in the project. But another issue is that it can get very out of date. It can really rot if it's, particularly if it's, so I guess particularly if it's far away from the code. So, I guess my perspective on it, and there's probably no right or wrong here, but I reckon that having sort of clear, readable, runnable code first is probably the main thing to help developers, and then sort of more proper documentation if you have time. And I guess a caveat to this is I'm sort of talking about internal documentation. So if you have users, then you're kind of going to have to write something for them. And I guess another piece of advice there is just that the documentation is less likely to rot if it's sort of closer to the code that it describes. Just because, I think people are more likely to be mindful of it, to see it and remember it, rather than if it's sitting over on some network drive somewhere. So, that's my view on documentation. Next up is continuous integration. This is the practice of integrating small changes frequently. And I think this graph that I stole is quite nice. It's from Martin Fowler, who's, I think, one of the original Agile Manifesto people. I guess the soundbite that goes along with this is, if it hurts, do it more often. And there's definitely areas of life where this doesn't apply. I think it often holds true in a software engineering context. So the observation is basically that many painful tasks become less painful if they're smaller, so as if you look at the curve, effectively it's saying that the pain increases non-linearly the longer the time takes. So if you're sort of if you're doing these, if you can sort of nip things in the bud by sticking close to that left-hand side of the curve, then you can save a lot of pain and effort. So now just looking at some specific benefits from continuous integration. So going back to that issue that I talked about before of merging. So mergers are much easier with continuous integration. There's much less chance of conflicts. And fixes aren't blocked by unrelated features. So, it's easier to release and deploy because at any given time your code is likely to have the latest sort of fixes and features merged into it. The code tends to be tested more regularly when you do those mergers. And it heavily reduces, what I think of as the code multiverse kind of issue. So basically, as I mentioned before, if you've got multiple branches, then in your repository, your code is effectively in multiple states at the same time, and so you have to be sort of thinking, oh, well, this branch has this feature and this fix. This one has this feature but not the fix, and this one has the fix but not the feature, and it can get, it's just a lot of mental effort. Just some caveats to that in terms of starting it. It does require a mindset shift in your team, and breaking things down is a skill that does require practice, and that's something that we are working on still in our team. And there is a need to put in some effort up front to refine your tasks, but tooling can make it easier. And so one of the things you can do is automated tests, which check code correctness. And a second order benefit to that is that tests are a form of documentation. They say the sort of code behaviors and invariants that we need to preserve when we make changes in the future. So basically a way for you to know if your changes have broken something important in the code. And also because they're code and they're sitting with the rest of your code, they're less likely to decay if we think about it as documentation. It's very, very important to run tests regularly and ideally automatically, and we'll touch on that very soon. So the other thing is automated analysis. So talking about things like linting and static analysis. Auto formatters to keep the style of your code consistent. So that's just one less point of variation. There are very good tools out there for most programming languages. They can find security and performance issues. They can educate developers. I think my code has improved a lot from the use of static analysis tools. And it also just reduces cognitive load by, again, hollowing out sort of the cosmetic issues and formatting and things, and can find very subtle issues, and just frees up the developer to focus on the big picture, which is things like architecture. So the last thing I want to talk about is pull requests. And a pull request is basically a request to integrate changes into the main branch. So it's a merge operation. And you can kind of think of it as a combined platform that brings together many of the best practices that I've talked about. So it's a platform for code review. You can leave messages on particular pieces of code to say good, or this isn't so good, or whatever. And it's asynchronous, so you don't have to be looking at it at the same time as the person who wrote the code. The pull request can be used to run tests and checks automatically in an isolated environment and in a way that's not skippable. So that helps to make those tests more useful, I think. And it's also a place to document details of the bug or feature that your changes are addressing. And finally, it protects the main branch. It's a sort of quality gating mechanism. And it can sort of constrain how people can merge into the main branch, which can get hairy with Git. So just to close up, so the right development practices can make development easier, less chaotic, promote good coding automatically. They can help get people up to speed and help them to learn and progress in their skills, and also just reduce cognitive load and make for a more sort of peaceful development process. And these practices all sort of feed into each other and work together. So the more of them that you follow, the easier it gets. And that's it from me. Thank you.
Thank you very much, Andrew. Do we have any questions from the audience? I actually have a question for you. You mentioned that when we are more familiar with something, it's less painful, and I find that's very true. I also see that that's often when people tend to take shortcuts. So there's a bit of tension there between those. Do you have any sort of suggestions on how people can be familiar with something, not painful, but without getting tempted to take shortcuts?
So could you give maybe just an example of that? Sorry, I didn't just.
So when we're more familiar with something, that's when we're tempted to take shortcuts because we know it. I'll save later. I don't need to save right now. Just any general advice for people to not fall into those traps.
Right. Well, I guess I suppose the heavy-handed answer is that you can constrain processes so that they can't really do that. So there's one nice thing about pull requests is you can be quite granular in what your requirements are about for code to be merged. So you can say that the tests have to pass, or it has to the static analysis can't find any issues, or it has to be formatted correctly. And yeah, you can't merge without that. And people can find that quite frustrating. So you have to have buy-in from your team on that. I think it has to be something that you work out in your team, and that will depend on the how close you are to sort of production code and the level of formality needed. But yeah, that's one avenue.
Excellent. Thank you very much. Please join me in thanking Andrew one more time. And now I would like to welcome up our next speaker, Andrew Littauer, for the talk on open source sustainability.
Hello, that was really exciting. For a second I thought Andrew was going to show up. My cousin, that would be really cool. I like him. He'd probably be fishing right now. So, hello, this is actually blank because it's blank in all your schedules. So just ignore this and pretend that this is an untitled talk. Why should you do that? Partially because I was asked to give this yesterday at random. I was cornered by Nick in the hallway. He offered coffee and to pay for my entire flight here. So thank him as loud as you can. He did not do that, but you still should see what happens. Anyway, this is me. So I had a whole thing on my laptop, which I realize is not out, where I was going to say words in Maori saying thank you all for being here. I think Kiora is about what I can remember. I come from Vermont, which is traditionally Wabanaki land, the Abenaki land of Ndakana, and I'm excited to be here. Who am I? I have no idea. So next slide. So I work at SustainOSS. Sustain is a community of people dedicated towards understanding what is open source and what are the structural systemic risks associated with open source. How do we keep the whole thing going? Open source is a methodology for coding. It's been around since the late 90s. There's been shared code a lot of time before, but the idea is you license your code so other people can use it. I hope that's not surprising to anyone. If so, this is going to be a very weird talk. Sustain is a community that started in 2017, I believe. We basically had a big conference where we're like, maintainers are burning out, and we don't know what to do about it. How do we make sure that we don't just continually build a horrible, horrible system where people put code in the commons, don't get any money for it, don't get any thanks for it, then end up leaving, and then we're stuck with really crappy infrastructure. This is still happening. So we had another conference and another one, and then COVID hit, and then we sort of went online to working groups. I was the person in the room who raised his hand and said, hey, I could do those. So I've been running a lot of those, including the academic working group. We have a podcast, SustainOSS podcast. I've recorded like 300 podcasts now with people about this topic, which is really exciting because it means that I have some authority in the sense that I've listened to other people talk and not understood a word they said. But that's one of the main outcomes of this. It's kind of cool. You may be wondering where sustainability applies in free and open source software, or FOSS, or FLOSS, or whatever you want to call it. Here are some of the things I'm going to break down. These slides here came from a talk I gave at FOSSI, the Free and Open Source Software Yearly Conference, which was aspirationally named last year, run by Software Freedom Conservancy in Portland, where I talked about how sustainability is a horrible word and you should never use it, which is silly because I work at an organization called that. But it doesn't mean much most of the time. It mainly means, can I have enough money to continue working? Which is great, but we should just say that. So looking at these things, what does sustainability mean for projects? It means growth. Never, ever means shrinking, which is really weird because often shrinking would be good. More in than out, pathways to a maintainership, product management would be excellent. Let's get more market share attention. For diversity, a lot of times you see sustainability mentioned. We're talking about welcoming spaces, COCs, diversity of actual, say, gender or race or a lot of other vectors of people contributing. For funding, most people talking about funding for the project costs, occasionally talking about funding the core maintainers to do their work. Occasionally we talk about lifestyle funding. How can I get to a point where I can work 2 hours a week and spend the rest of my time mountain biking? Not a joke. And things like funding for all contributors. This is all leading up, by the way, I realize I didn't say this at the beginning, all leading up towards me talking about how we can think about sustainability in a New Zealand context, looking at university academic open source program offices. So keep in mind, this is all relevant to what you're doing, I hope, but I haven't talked to many of you because obviously I don't have a New Zealand accent. So I have no context for what's going on. This is what I know. Developers, when people talk about sustainability, they're talking about satisfaction, career trajectories, mentoring, mainly avoiding burnout. For communities, it's pretty much the same. We want to make sure the entire community is healthy and growing. Health is often not broken down with appropriate metrics. So oftentimes it just means, again, are the maintainers not burning out? Businesses is really interesting. When we talk about sustainability for open source from a business perspective, we're often talking about, is my bottom line going to be affected by the open source that I'm using? And how can we avoid that? But we're often talking about this word right here, which is OSPOs, Open Source Program Offices. Open Source Program Offices is a new concept where you have someone in a business whose job it is to field questions on open source. And it's their job to figure out, okay, how can we make sure that open source is happening here, and how can we make sure that open source is like being used in the platform, in the business. Often really means inner source. So how can we use open source methodologies internally to talk between different groups at Google, because they don't know how to talk to each other, which is kind of funny. Recently, OSPOs have switched into academia, which is what I was hoping to talk about. This is a really fun slide. So the impact of open source on the ecosystem at large is massive, and these are two papers. One's from OFE, Open Forum Europe, which says that $65 to $95 billion of the EU's general GDP is enabled by open source right now. So that's like the price tag you can put on it. So people say, do we have to make open source commercially accessible to, say, CRIs? You can say yes, because it's really clearly evident by this paper from OFE. And a paper just came out a month ago from Nagel at Harvard and his collaborators, that there's trillions of dollars on the demand side for open source. Again, I would really contextualize this within a New Zealand context. When you talk about why should I go open source at all, everyone you're talking to should be able to see, oh, there's money in it, which is weird because right now that's not what they think. That's kind of fun. Go read this paper. It's a cool paper. So ecosystem, let's just skip that. AI is going to be big. Skip that. I saw this on a dumpster and I thought it was excellent. Who will stop GPT? Sometimes when we talk about sustainability, we talk about the environment. It's a whole different question. How do we avoid like the cost of everything? How do we keep carbon costs down? And sometimes we talk about use of tech as a whole. So I mentioned all that. That's what I talk about when I talk about sustain. A lot of the times when I'm talking about it, I'm actually talking about academia, because I'm working with academics a lot to talk about what is sustainability for open source, what we just covered, all those different aspects. I just wanted to give you a background about what it means in open source. How do we understand that within an academic context? So I have a monthly meeting group that we have. 25 people on average come to those calls, but our membership of lurkers is much higher, which is kind of nice. And we have a mailing list and all that sort of stuff. And we talk about how can we do this in an academic setting. So when I'm talking about open source in academia, one of the meetings we had 4 months ago, we came up with this document. These are all the different ways we talk about that. So one of them is we talk about research software. Just had a wonderful talk about RISA next door by George. I'm sure a lot of you are familiar with RISA. Talk about what that is, and we talk about how do we make sure that that continues, that we keep making research software, and that people are recognized for their work. One of the main problems is that when we think about software as a dependency for those research software engineers, you don't often think about the fact that it's the university's job and academia's job to actually make sure that invisible dependencies are also taken care of. Everyone who's working on open source is standing on someone else's shoulder. And right now, none of the people who are, say, working on curl are getting any benefit from anyone working at, say, the University of Otago. As far as I know, unless someone's paying Daniel, which is great. So someone should, right? Excellent. So that's something we can think about when we think about, well, academically, what should we do as academic institutions, as research institutions? Should we be paying it back as opposed to just saying, open source is great, and then not giving anything back downstream? We think about open source software. I kind of just covered this by accident, but it works out. All these things cover over. The Venn diagram of this would almost be the one ring. Teaching material. So sometimes you're seeing open source now being used actually in courses to undergrads, which is really, really cool. There's a master's degree on open source business management. Really interesting title at Brandeis. JHU has a course where they teach open source entirely. I think it's actually now at CMU. Sorry, that's Johns Hopkins University and Carnegie Mellon University. Generally, they're pretty rare, but they could be useful for fostering collaboration. I talk very fast, and I put a lot of parenthetical comments in. Nothing I can do about that. EdTech, most universities are using open source actually in the university itself, which is really interesting. So how do you do scheduling for all the student courses? A lot of times you have university spin-outs. This is less common here, but you basically have some students who work on open source, maybe with a professor, then they go and make a company out of it. This does happen, and I would love to have more examples of this. One of them that might be good is Ceph, C-E-P-H. Ceph started with a student at UC Santa Cruz who went out, did his PhD, realized he could make a company out of it, made a company out of it, made a lot of money, donated millions of dollars back to UC Santa Cruz, and now there's more PhDs and master's students there working on open source. That is super cool, and I really like that. And there's other examples of universities paying or being paid by industry together. I just learned that SAP and Alliander in France are doing that. Akamai is another one that came out of MIT, became a public company. CROSS is what I just mentioned. CROSS is the Center for Research on Open Source Software at UC Santa Cruz, which was funded by the guy who made Ceph. OSS is also, of course, a research subject. Tons and tons of papers on it. It's also a research object, which we should all cite and we should all use and we should all submit to JOSS. Is that 5 minutes or seconds or hours? Excellent. JOSS is the Journal of Open Source Software. Very, very exciting. These guys have figured out a hack where if you just put anything in a PDF, other people can cite it. And now it's actually quite a nice journal. They get an average of 2 submissions a day, I think, from open source projects at the moment. So thousands of research objects have now been created, which are basically full journal articles, which help for tenure, which is maybe less important in New Zealand. I don't know the context as much, but certainly important for, say, is my job good? Yes, we should keep paying you. Funding landscape's really interesting. I'm more familiar with the American side. What I was hoping to talk about here wasn't so much that there's philanthropies that are interested in paying for this sort of stuff. I know some of us in the room have been funded by philanthropy. I'm funded mainly by Sloan. But more that around the world there are funders who are interested. Carol Goebel, who just left, is a good example of an awesome funder. The International Funders Workshop, everyone there was interested in how can we fund open source, which is really cool because that means hypothetically that New Zealand could corner some of that market by saying we do X really, really well. I wish I had more to say about CRIs here because that seems to be a lot of the blocker for why open source hasn't worked. But I don't, so meet me after class. And then there's all sorts of things that are related to the academic setting that are important when you think about open source in an academic setting. So open work, open design, open governance, there's all sorts of open things. In fact, one of the largest university units interested in open source work is technically just open work in general. That's at the University of Rochester, RIT. Security is big, AI should be in this one. So that's a lot of content. And that's a lot of context. It's like too much. Like any one of those slides could have been a thesis. But open source program offices is a way that some Americans and Europeans have figured out, oh, if we have someone at the university whose job it is to explain that to people who don't have the time to figure that out, it works really well for us. And so instead, let's just hire someone who we can throw questions at. And what's really cool is that these people are now getting funded. So the Open Source Program Office, or OSPOs, I'm going to say because it's much faster, started at JHU, Johns Hopkins, and RIT and CROSS. I think Johns Hopkins was the first. That was around 4 or 5 years ago. There's now over 10 of them. A lot of them have been funded by Sloan, which is a large philanthropy that was initially General Motors. GM, the guy who made General Motors, put a huge money into an endowment, skim off the top, let's just give this to people for science, big S. This is really cool because these people are talking to each other and they're doing so in a network called Curious, which is the community for university and research institutions on open source software. I also co-run that one, which is fun. So we also have monthly meetings because it's easier to just copy what you did in the other community. And we're talking to universities all the time about, hey, I have students, I need to teach them. Hey, I need to collaborate. Hey, I need to figure out how to get my postgrads funding. Hey, I need to figure out how to work with the GPL license in my university. And so all these questions are being asked and answered collaboratively in this group, which is really, really fun and something I wanted to do or talk about here. I haven't met a ton of people here who are working at a university at a level like of the vice provost office or the provost office. All of the universities in Curious, of which there are a ton, have all managed that. And that's really nice because they're bringing money into the university. Some of them are cash positive. Cross is cash positive. So more money comes in than is being given to them by grants, which is excellent and super, super cool. You may recognize some of these names. Penn State, Stanford, Syracuse. UVM is up the road from me. They have a meeting happening right now that I said I would go to, and then I accidentally came to New Zealand, which is great. This is what, when we're talking about OSPOs, and we're talking about being an OSPO officer, the person in charge of an OSPO, these are the slides that you show to other people to make them understand what you do, which is really cool. So we're talking about excellence in OSS. Everyone wants that because we want to have more clout, we want to have more share and more market buy-in for attention in the IT economy. Research impact, working with communities, I think would be its own section in New Zealand. It's not where I am because we're not very good at that in my country. But I think that's actually equally important here, working with the iwi, et cetera. Skills and education, everyone likes that. Internships is great because you can do it directly with businesses, which can bring money back to the university. And then operations, just making sure that things actually work, which I think is where collaborating with things like Nessie would work really, really well. So framing this and figuring out how to pitch this in 2 minutes would be good. And that was basically the story I wanted to tell. I was going to say at the beginning, please interrupt me, but I forgot. But tēnā koutou katoa, and let me know if you have any questions. Thank you.